In this video, we will be looking at coordinate transformation. And of course, it is a fundamental operation in analytical geometry, and these transformations can include rotation, translation, and scaling. It helps us manipulate and analyze geometric shapes by changing the reference frame and perspective. So we can have them in 2-dimension or 3-dimension, that is 3D. So talking about the applications, particularly in engineering design, they find very useful applications in robotics, in computer-aided designs, and so on. And okay, let's look at rotation in 2-dimension, 2D. That basically involves turning a point around the origin by an angle theta. So let's say you have a point on a coordinates, let's say the point P, and you have X and Y axis. There are some engineering designs that often require turning this point around by an angle, and that will lead to the rotation of x-axis, so a new point entirely, x prime, and rotation of y-axis to a new point entirely, y prime. So when this happens, of course, there are various situations in engineering where this can happen. Take, for example, you've got a robot. Various machines use the principle and design of a robot. Take, for example, an excavator working on a construction site. Okay, my drawing might be bad, but just never mind. Let's just see how we can quickly explain that using the design of a robot. Okay, now this is the origin, and this point is movable, and let's say we've got a fork, and let's say we've got a building at this point. Okay, please never mind my freehand sketch. All right, so now this robot wants to lift these buckets from this point to this point here, say point A to point B, and point A to point B. Now that would involve this robot taking these buckets and moving from this origin to this point, and of course moving it in this direction. So what we are trying to say is that in different engineering field, such kind of design or programming is very applicable, in that warrants movements of an object which will require rotation about a point, or movement about the origin from one point to another. Now, away from there, basically, as a general rule, of course, this can be proven, but we don't really need to go into that. So, as a general rule, the new x coordinates formed as a result of the rotation in two-dimensional plane would equal to x cos theta. So theta is the angle that the new x-axis forms with the original plane. So the new y-axis now equals x multiplied by cos theta minus y sine theta, and the new y-axis will equal x sine theta plus y cos theta. All right, so take for example, if a point P has these coordinates 2 and 3 and is rotated by an angle of 45 degrees around the origin in 2D. So let's find the new coordinate of P. So basically, just by identifying the coordinates and the angle, of course, this is the y x points on the two-dimensional plane. This is the x and y points, coordinates. So just basically plug in these values, and this is the angle theta of rotation. So just basically plug in these values into this general equation here, will give us the new coordinates of P after the rotation. So that gives us x prime equals 2 cos 45 minus y, which is 3 sine 45, which is the angle theta. All right, so the new y axis will equal 2, which is the x there, sine theta, which is 45 degrees, plus 3, which is y cos 45. Now, of course, you know, basic angles, trigonometrical ratio. Of course, sine 45 is 1 all over root 2, and sine 45 equals 1 all over root 2. So just playing around with that equation gives us minus 1 all over root 2. Of course, this can be rationalized, and we can decide to leave it this way. The same thing applies here. Playing around with this gives us 5 all over root 2. We can also rationalize this, or as well leave it this way. So now the new coordinate of P will then become minus 1 all over root 2 and 5 all over root 2. All right, so of course, rotation can also be done in space, that is 3D. So take for example, let's just look at this example. Of course, just a little difference between rotation in 3D and rotation in two-dimensional. So the new points, as a general rule, particularly if the rotation is done along the z-axis, the new coordinates will form x prime being equal to x cos theta minus y cos theta. The new y axis, y prime, will be x sine theta plus y cos theta, and z remains unchanged because it is rotated along the z axis. So now let's take for example a point P, 3D of course, x, y, z, is rotated by 90 degrees around the z-axis. So determine the new coordinate of the point after the rotation. So the solution to this is simply plugging in the values of the coordinates and the angle into this general equation for solving the problem, and just playing around the equation. Now, given of course x, y, z to be 1, 2, 3 as we've got here for point P, and the angle of rotation 90 degrees. So now plugging that into this general equation for such kinds of problems, 3D kind of rotation. So where cos 90 equals 0 and sin 90 equals 1. So plugging all these values in the equation will show that point x prime equals -2, y prime equals 1, and z prime equals 3. Of course, that remains unchanged. So the new coordinates of the point after the rotation are p prime equals -2, 1, and 3. Away from rotation, we can also have such transformation in form of translation from one point to another. So basically it involves a shift by a certain distance along the x and y axis, and you can have it in this form. So this is, let's say, a point Q, and this is the origin. And when there is a shift, and such shifts, translational shifts, involves movements, entire movement from one origin to another. So the new point Q prime now, so this becomes entirely shifted from here, from the initial point here to here. So, and we've got the y-axis, y prime. So this kind of shifts by a distance x is called translation. Now, so if a point xy is translated by change in x, of course, along the x-axis there is a change, and along the y-axis, of course, there is a little movement, maybe horizontally, upwards, as the case may be. Of course, change in y can be 0, it can be any number, as the case may be. So now, if there is such translation that leads to a shift in the x-axis by the x, and a shift in the y-axis by the y, delta y, or change in y, as the case may be. So now, the new coordinates x prime and y prime are given by simply adding the change in x to the initial coordinate of x and change in y by the initial point on the y-axis. So now take, for example, a point Q, 5, 1, that is x equals 5 and y equals 1, is translated by a vector. 3 and -2. So now let's find the new coordinate of Q. So just simply plugging in these values with the translation that occurred along the x and y axis, of course this vector here. So it shows that 5 plus 3 will be the new x-axis, and 1 plus -2 will be the new y-axis, and that we've done here. So the new coordinates of Q will then be equal to 8 and -1. And of course, usually we can have a combined transformation taking place in any system, in any engineering system or thereabout. So now let's consider still under some two-dimensional plane. So let's apply a translation of 3 and -2, followed by a rotation of 30 degrees around the origin to the points. So this is the origin, P. What are the final coordinates of the point? So the first transformation that occurred on this point was translation, then followed by a rotation. So the new point will definitely become, so first thing to do is to perform the translation operation on these points using this general equation. So when we translate this initial point by this vector, what we've got is adding 5 and 3 for the new x-axis, and 1 and -2 for the new y-axis, and that gives us 8 and -1. Of course, that was very similar to what we did here. So now after getting the new point, the member or the point was now rotated by 30 degrees. So what we then do is to now use the rotation technique. We perform the rotation operation on this point. So, and of course, the angle of rotation is 30 degrees. So what we just do is recall the general equation mentioned earlier. And of course, this position, of course, you can see it is P prime. So because we are talking about a combined transformation here, so after the next transformation, which is rotation on it, we will have to represent our coordinates as prime, because this is the second transformation happening on that point. So the x prime now will be x, which is 8 multiplied by cos 30, minus y, which is -1, times sine 30. So the y coordinate will be x, which is 8 multiplied by sine 30, plus y, which is -1, times cos 30. Cos 30 is square root of 3 all over 2. So we just play around this equation to arrive at the coordinates for x and y after the second transformation occurred at a point. So, and that gives us the new coordinates to be 7.42 and 2.27. So similarly, translation can occur in space, that is 3D, and where we have the coordinate points x, y, and z. So as a general rule for translation in 3D, the new x-axis, y-axis, and z-axis can be determined by simply adding the change in x-axis, the change in y-axis, and the change in z-axis respectively. So let's take, for example, a point Q with this axis, with this coordinate is translated by the vector 2, -1, and 4. So find the new coordinates of the points Q. So what we just do is simply add up each of the coordinates with the translated vector for each. So that will mean 1 plus 2, 2 plus -1, and 3 plus 4. Now that has been done here to arrive at the new coordinates of Q. So the new coordinates of Q are 3, 1, and 7. So another example here, translate the point P with coordinate 2, -3, and 5 by the vector 4, 7, and -2. So what are the new coordinates of the points after the translation? So basically the new points are just to add the corresponding changes in x, y, and z, and that will be by adding 4 and 2, 4 and 2, -3 and 7, as well as 5 and -2. So playing around with that shows that the new coordinate of P will give 6, 4, and 3. Alright, so coordinates transformation can also occur in form of scaling, and that has to do with changes in size of an object by expanding or contracting it along the x and y direction, that is in two dimension. So if a point x, y is scaled by a factor sx and sy, that is xs being in the direction of x and sy in the direction of y. So the new coordinates, simply put, will be multiplying the factor along the x-axis with x and the factor along the y-axis with y. So take, for example, a rectangle has vertices at A, B, C, and D, and these are the vertices 1 and 2, 4 and 2, 4 and 6, and 1 and 6. Now scale the rectangle by a factor of 2 in the x direction and by a factor of 3 in the y direction. So find the coordinates of the new vertices. So the solution as described by this general equation here. So the solution will simply mean we multiply in the x direction 2 by all the x axes, and that will be 2 multiplied by 1 for vertex A, 2 multiplied by 4 by vertex B, 2 multiplied by 4 for vertex C, 2 multiplied by 1 for vertex D. And relatively, we multiply the factor 3 by 2 for vertex A, 3 multiplied by 2 for vertex B, 3 multiplied by 6 for vertex C, and 3 multiplied by 6 for vertex D. So that is what we've done here, and the new coordinates of the vertices are after scaling, are the new vertices as calculated. Scaling can also occur in space, that is 3D. So, and if that happens, similar to what is obtainable for a three-dimensional plane, so we simply just multiply the factor, the scaled factor along the z-axis by the points z, the coordinate point z. So let's take as an example, a cuboid has dimension 2 by 3 by 4. So scale the cuboid by 2 in the direction x, 0.5 in the direction y, and 3 in the z direction. So what are the new dimensions of the cuboid? So what we do here is just to multiply each of the factors in the corresponding directions with the coordinates of that direction. So that will be 2 multiplied by 2, 3 multiplied by 0.5, and 4 multiplied by 3. And that is what we've done here. Now the new dimension of the cuboid after scaling are 4 by 1.5 by 12.